Hello, yes. In this session, I am going to explain that one more colligative property, depression in freezing point. Okay. In the previous session, we studied about elevation in boiling point and the mathematical expression and the graphical representation we studied. Now let us see that depression in freezing point. To understand about this depression in freezing point, first you must be know about what is the freezing point. Here I am given that exact definition of freezing point. You can see that the temperature at which vapor pressure of liquid state equals to the vapor pressure of solid state. That particular temperature we are taking as a freezing point. Okay. You know that the freezing point and boiling point we related with that vapor pressure. Okay. So when we studied about that vapor pressure of pure solvent and vapor pressure of solution, when we compared that vapor pressure of pure solvent always is greater than to the vapor pressure of solution. So this thing already you know that based on this one vapor pressure we related that boiling point and freezing point. Okay. So what we observed when we studied about that pure solvent, volatile solvent when we studied. Okay. When we taken that pure solvent, so here we have the more number of volatile particle. So we are expected the more vapor pressure. For this pure solvent, when we are added a non-volatile solute, okay, so when you are added non-volatile solute, so what happened? The solution vapor pressure is going to decreases, okay, and vapor pressure when decreasing, boiling point is going to increases. When boiling point is going to increases, the freezing point is going to decreases. So that information already we discussed in the previous sessions here. Okay. So when you observe that the curve with respect to this freezing point, okay, here I am explaining that the curves with that vapor pressure, okay. So here I am taking that the vapor pressure and freezing point you can observe. So temperature. So when you observe that, generally the solid vapor pressure curve I am taking here. Okay, so generally it is containing that when the temperature is decreasing, the vapor pressure is going to decreases. Okay. Now, when you are taking with that a pure solvent, so pure solvent vapor pressure usually more. Okay. So pure solvent vapor pressure is more. When temperature decreases, what happens? The vapor pressure is going to decreases. So at this particular point, okay. So this is I am given with respect to that a pure solvent. This is the pure solvent. Okay. So when temperature decreases, what happens? The vapor pressure is going to decreases. So this at this particular temperature, what happens? The vapor pressure of pure solvent, which is existing in liquid state. Okay. So this is I am given that solid curve. This is that. Okay. When it is a solid, the curve is representing in that block. Here that liquid you have that a pure solvent vapor pressure usually greater. When temperature decreasing, the vapor pressure is going to decreases. So at this particular temperature, okay, so what happened? The pure solvent vapor pressure is in liquid state is going to equal to the solid state. So this temperature what I am given the freezing point. Okay, so freezing point of pure solvent. Okay, T naught F I am representing, this is the freezing point of pure solvent. When I am added a non-volatile solute, what happens? Vapor pressure is going to decreases. Okay, assume here the vapor pressure is there. This is the vapor pressure of solution. This is the vapor pressure of solution. Okay. So when temperature decreases, what happens? This is also going to decreases. Okay. So at this particular temperature, what happens? The vapor pressure of solution is going to equal to the vapor pressure of solid solution. So this temperature usually we could call that okay, freezing point of solution. I am showing with the TF. Okay. So that means when you are added a non-volatile solute to the solution, so what happened? The freezing point is going to decreases. This freezing point is going to decrease. So this depression in freezing point, I am showing with the delta TF. Okay, I am showing with the delta TF. So what is the delta TF? delta TF is equals to T naught F minus TF. Okay, delta TF is equals to T naught F minus TF. What is the T naught F? Freezing point of pure solvent. This is the freezing point of pure solvent. Got it? Okay. So generally we are taking the volatile solvent. What is the TF? Freezing point of solution. Freezing point of solution. So this is the depression in freezing point. When we are adding a non-volatile solute to that volatile solvent, the freezing point of solution is going to decreases. Okay. So here freezing point of solvent is usually greater. And you know that generally these colligative properties majorly depends on which one number of solute particles. Or nothing but we are taking that delta TF is directly proportional to concentration of solute. Yes or no? Okay. So these colligative properties majorly depends on that concentration of solute. So usually here the concentration of solute we express it with respect of molality. Okay, so that's why I am given the delta TF directly proportional to F. When you remove the proportionality, what you get, the delta TF is equals to KF into M. Okay, delta TF is equals to KF into M. Otherwise, it is also possible to write delta TF is equals to KF into WB by MB into 1000 by WA. Okay, so what is the WB? Weight of solute. What is the MB? Molar mass of solute. And WA is the weight of solvent. So here KF is a cryoscopic constant or molar diffraction constant. Okay, KF is equals to molar diffraction constant. Or we could also call it as cryoscopic constant. Cryoscopic constant. Okay. So usually for water Kf is equals to 1.08 okay degree Kelvin for molar we will be take that. So Kf is equals to molar depression constant or cryoscopic constant. So here also we have that expression for Kf. Okay. So how we could find out that Kf? So Kf usually we are taking with respect of here. Kf is equals to R TF square by 1000 into LF. Okay. Kf we are calculating by this formula. Kf is equals to R into TF square by 1000 into LF. So R is equals to, you know, that universal gas constant. TF is equals to freezing point of pure solvent. Freezing point of pure solvent. And LF is equals to latent heat of fusion. Latent heat of fusion. Okay. So this is LF is equals to, we will be taking that delta H fusion by the molecular weight. Okay. So if you are substituting that LF in this one, finally you got that expression for Kf is equals to R TF square by 1000 into LF. But we are taken delta H fusion into molecular weight. Okay. So this is the expression for Kf. Got it? So units for Kb and Kf both are same. Okay. So generally Kb for water is 0.52 and Kf for water is 1.86. Usually we have taken that. Okay. So this is the expression for Kf or Tf square into Mw by 1000 into delta H fusion. Okay. So units for Kb and Kf, what we are given that. So generally we are given degree centigrade molar inverse or Kelvin molar inverse. Units for Kb and Kf both same, you will get that. Okay. Otherwise degree centigrade mole inverse Kg or Kelvin mole inverse kg. Okay, so units for kf, both kV also have the same units. Okay, so this is the depression in freezing point. So this is the delta Tf is equals to Kf into m. By using this, it is possible to calculate the molar mass of solute. Got it?